Hello students, welcome to video lecture on partial differentiation. Already I have taken 7 video lectures. In that 7 video lectures I have discussed these topics, that is partial differentiation, successive differentiation, total differential, exact differential, theorems of differentiation, chain rule and change of variables from Cartesian to polar coordinates, and also covered some examples on that. Now, in this video lecture, I am going to discuss condition for maxima and minima of a function. Now, let us go for that. Conditions for maxima and minima. So, let us take f, that is function of x, suppose. And if we plot graph of f of x versus x. So, on horizontal axis, I have taken x. On vertical axis, I have taken f of x. And suppose we have function in such a way that we get graph like this. So it is varying graph, and that is according to whatever mathematical function of f, that is f of x. Now let us take different points on the curve. So point A corresponds to this value of x, point B corresponds to this value of x, point C corresponds to this value of x, point D corresponds to this value of x, and point E corresponds to this value of x. So these are different values of variable x, and corresponding to that values f of x has, means here this is value of f of x here we have f of x, it is this one. So here corresponding to point C, corresponding to point A, you will get f of x here, corresponding to point B, you will get f of x here, corresponding to C, you will get f of x here. Now let us take point A and draw tangent at that point. Now if we see here tangent, it is straight line, and here at point A tangent has some slope. So what is that slope? So if we take here df by dx, that is slope of the tangent at point A, means I can take corresponding to suppose x0. Now here tangent, it is greater than 0, means function is increasing. We have here another point D. Let us draw tangent at this point. So I will take this as x1, x2, x3, x4. So tangent at point D means tangent at point x3. And if we see tangent, its slope df by dx at D, means at x3, it is less than 0. So function is decreasing. Function is decreasing here. Now we can draw slope at tangent at point B. Now tangent at point B, it is horizontal one. So slope of this is horizontal one. Slope of this, that is df by dx at point B or at x1 is equal to 0. If we take here at point C, and if we find its slope, so df by dx at point x2 means at C is also equal to 0. If we take point E and draw tangent here, we will observe here df by dx at point E means at point x4 is equal to 0. So we have 5 points. At A slope is positive, at B slope is 0, at C slope is 0, at D slope is negative, and at E slope is 0. Now, according to Fermat's theorem, What is that Fermat's theorem? According to Fermat's theorem, if f of x has local maxima or local minima at a point x is equal to a, then f dash a will be equal to 0 at that point. F dash a means first order derivative, that is slope. So here point B, point C, point E. So these points are also called extremum points. Extremum points. Now point B, point C, point E, at these points slopes are 0. But one point may be maxima, another point may be minima. So how can we decide whether that point is maximum or that point is minimum? So here the points are called stationary points. Stationary points means when df by dx first order derivative at a point on the graph is 0, that point is called stationary point. So here we have x1, x2 and x4 are stationary points. Whether that is minimum or maximum, that is decided by second order derivative. So because at all these points at B, C, E, first order derivative is 0. So if we take second order derivative, so we know df by dx is equal to 0 at stationary points. Stationary points. Then we can have second order derivative d2 f by dx square. Now d2 f by dx can be 0. Second, d2 f by dx square can be less than 0, that is negative. And third, d2 f by dx square may be 0 or in conclusion. If first order derivative is 0 and second order derivative it is greater than 0, that is positive, the point is called minima. Minimum. So that represents minimum of the graph, local minimum of the graph. If second order derivative is less than 0, negative, it is called maximum. And when second order derivative is 0 or inconclusive, it is called point of inflection. Point of inflection. So here, if we see in the last curve, you will see at this point, second order derivative will be greater than 0. At this point, second order derivative will be less than 0. And at this point, second order derivative will be equal to 0. Now, if we see here, this is minima. And if we see points on both sides of this minima here and here, you will observe here df by dx is less than 0, and at this point df by dx it is greater than 0. Here also, if we take 2 points about C, here if we draw tangent, you will get df by dx, it is greater than 0, and here df by dx at this point, df by dx, it is less than 0. So here about maxima or about minima, on one side df by dx will be greater than 0, on another side df by dx will be less than 0, means positive and negative. But if we see this point E, so if we see, I will show that point again here. So if we see the curve is like this, curve is like this, and this point is E, and here tangent is horizontal. So first order derivative is 0, second order derivative is 0, and if we draw, suppose point, if we take point here and draw tangent and find slope, it is less than 0. If we take point here, here also slope, it is less than 0. You can have point graph like this also. Here point E, at this point if we draw tangent, slope, it is greater than 0. If we draw tangent here, slope, it is greater than 0. So about point on both sides, slope will have the same sign. So this point A, it is point E, it is called point of inflection. It is called point of inflection. So this part, it is called concave up, and this is concave downwards. Concave down. So in this way, we can find minima or maxima or point of inflection of a function f of x using these conditions. But suppose we have function like this, f is equal to f of xy. So function of two variables. Then how can we find maxima and minima of two variable functions? So here we have f is equal to f of xy. Then we find here fx and fy. Fx means dabba f by dabba x, and fy means dabba f by dabba y. Now, if both are 0, then xy is called, suppose at x0, y0. Both are 0 at x0, y0. Then x0, y0 is called saddle, uh, critical point. Critical point. Critical point. Or you can say stationary points. Stationary point. So it is critical point. Now that critical point may be minimum, may be maximum. So what is condition for that? So find fxx, fyy. Fxx is dabba to f by dabba x square, and here dabba to f by dabba y square, and fxy. This is dabba to f by dabba y dabba x, or f of yx, dabba to f by dabba x dabba y. Now if f is potential function, we know fxy will be equal to fyx for potential function. So here find second order derivatives, partial derivatives fxx, fyy, and mixed partial derivative. Then here at critical point, if fxx into fyy, it is greater than, means here we can take here uh, if here fxx and fyy both are positive and fxx into fyy product of these two, it is greater than fxy square, this one, then fxx and fyy both are negative and fxx into fyy it is greater than fxy square, and third fxx fyy less than fxy square. So here if fxx and fyy both are positive and fxx fyy greater than fxy square, then the point is called minima. Minima. So x0 y0 is minima. If xx and fyy both are negative, but fxx into fyy is greater than fxy square, it is called maxima. Maxima. And if fxx into fyy is less than fxy square, then x0 y0 is called saddle point. It is called saddle point. So for function of two variables, we can find maxima, minima, or point is saddle point using this one. Means take first order derivatives. If they are zero, the corresponding point is critical point. Then find out second order derivatives fxx, fxy, and mixed partial derivative fxy, fxy, and compare them by these conditions. And using these conditions, you can find whether that point is minimum point, maxima, or minima, or saddle point. Now let us take some examples. Find the position and nature of stationary points of the function. So here function is given f of x, single variable function, x cube minus 3x plus 3. So first condition we know df by dx. Now if we find df by dx, here it is d by dx of x cube minus 3x plus 3, and here it is 3x square minus 3. So I can write this as 3x square minus 1. This is df by dx. And suppose we want to find stationary point, then we have to equate this derivative equal to 0. So for finding stationary point, equate df by dx equal to 0. So here 3x square minus 1 is equal to 0. This gives you x square minus 1 is equal to 0. Now x square minus 1 means it is x minus 1 into x plus 1. And this is equal to 0. So x is equal to minus 1 or x is equal to plus 1. So we got 2 points. Now x is equal to minus 1 is minimum or maximum, x is equal to plus 1 minimum or maximum, that we can find using second order derivative. So I can take for x is equal to minus 1. What is d2f by dx square? Now d2f by dx square, df by dx is this, so 6x. So it is minus 6. So d2f by dx square, it is less than 0. So x is equal to minus 1 is local maxima. So we will get local maxima of the function at x is equal to minus 1. And if we take for x is equal to 1, what is d2f by dx square? It is 6x means it is 6. So d2f by dx square, it is greater than 0 means x is equal to 1. At x is equal to 1, we get local maxima. Sorry, here local minima. Local minima. So in this way, we can find local maxima and local minima of the function. Now let us go to another example. This example I have taken from this. So here f of xy is given, that is equal to x cube plus 6xy plus 3y square minus 9x. And what is problem? Find the critical points of the function f of xy is equal to x cube plus 6xy plus 3y square minus 9x and determine their nature. So here I will take f is equal to f of xy is equal to x cube plus 6xy plus 3y square minus 9x. This is f of xy. So we have to find first order derivatives. So let us take fx. So what is fx? Fx is dabba f by dabba x. Now if we take x cube plus 6xy plus 3y square minus 9x and differentiate partially with respect to x. So y is constant for this. So we will get what? 3x square plus 6y minus 9. So here derivative of this is 0. And fy is equal to differentiate with respect to y. So dabba f by dabba y is equal to. Now derivative of first term is 0. Derivative of second term with respect to y is 6x. And here 6y and derivative of this term is 0. So we'll get 6x plus 6y. So we got fx and we got fy. When we want to find critical points, we have to equate first order partial derivatives equal to 0. So let us equate this equal to 0 and this equal to 0. Now here from this I will get 3 is here x square plus here plus 2y minus 3 is equal to 0. So just divided by 3. Just divided by 3. And from this I will get 6x is equal to minus 6y. This give is equal to x is equal to minus y. So use this x is equal to minus y or y is equal to minus x in this equation. So if we use in that equation, we get 2 square plus. Now here 2 minus x minus 3 is equal to 0. So we get here x square minus x minus 2x minus 3 is equal to 0. So we can write this as x square minus 3x plus x minus 3 is equal to 0. So x into x minus 3 plus x minus 3 is equal to 0. So we get here x plus 1 into x minus 3 is equal to 0. So from this I will get x is equal to minus 1 and x is equal to 3. Now if x is equal to minus 1, then what is y? Y is equal to, I will get y is equal to 1. And if x is equal to 3, I get y is equal to minus 3. Minus 3. So we have 2 points. 1 minus 1, 1 and 3 minus 3. Now we'll check whether these points are minimum or maximum. So for that purpose, we have to find f x x, f a, y y, and f x y. Now f x x is equal to f x x is equal to, here fx is equal to 3x square plus 6y minus 9. So you will get here 6x. Fy y. So here derivative of first term is 0. So you will get only 6. And fxy. So you can differentiate, or fyx. So if we differentiate with respect to x, we will get 6. And at minus 1, 1. So we'll get here minus 6. Minus 6. So you will observe here f x x into f y y. Minus 6 into minus 6. And here it is 6. So it is equal to, means here f xy square. Now this is negative, so it is less than this. It is negative. Minus 36 less than 36. So I can say minus 1 1 is saddle point. Minus 1 1 is saddle point. Now for this one we can find now. What is fxx? 6 into 3. 6 into 3, that is 18. Fyy, that is 6. And fxy, that is 6. So this is positive. This is positive. And if we take fxx into fyy and fxy square. Now if we compare these two, you will observe that fxx, it is into fyy, it is greater than fxy square. So this 3 minus 3 is local minima. So it is local minima. So in this way, we can find critical points of a two variable function and we can determine their nature also. So here, this is about critical points. Now we'll go to implicit and explicit functions. Suppose we have function like this, f of xy is equal to 0. Then from this function, you can express y in terms of x. So if you are able to write equation for y in terms of x, then that function is called explicit function. But if it is not easy to separate y from x, then that function is called implicit function. So example for implicit function is e raised to xy minus sin xy is equal to 0. So you cannot write y is equal to something in terms of x. Such a function is called implicit function. So though the function is implicit, we can find dy by dx. So how can we find dy by dx? So we can use chain rule for that. Now here af is equal to 0. So if we take df by dx is also equal to 0. Means here df is equal to 0. So df by dx we can take 0. Now df by dx using chain rule. It is dabba f by dabba x into dx by dx plus dabba f by dabba y into dy by dx. Now df by dx is equal to 0. So we can write this as 0 is equal to dabba f by dabba x plus dabba f by dabba y into dy by dx, because dx by dx is 1. So we can write here dabba f by dabba y into dy by dx is equal to minus dabba f by dabba x. So dy by dx is equal to minus dabba f by dabba x upon dabba f by dabba y. So in this way we can find dy by dx, though we are not able to separate x and y. So here this is method to find derivative dy by dx, and this dy by dx represents tangent at some point, slope of tangent at a point. Now let us take example. So we can find here using this. If x cube plus 3xy square minus y cube is equal to 0, show that dy by dx is equal to minus x square plus 3y square upon 2xy minus y square. Now here this is implicit function. So here I can write f is equal to x cube plus 3xy square minus y cube. So dabba f by dabba x is equal to, I will get 3x square plus 3y square, and dabba f by dabba y is equal to, now if we find here 3y square x, sorry, dabba f by dabba y, that is 6, sorry, uh, we are taking dabba f by dabba y. So here 3x into derivative of y square, that is 6xy minus 3y square. And what is dy by dx? Dy by dx, we take this as minus dabba f by dabba x upon dabba f by dabba y. So we get here dy by dx is equal to, now dy by dx is equal to minus 3x square plus 3y square upon 6xy minus 3y square. Now we can take 3 common from numerator and common from denominator, and we can cancel that. So we get here minus x square plus y square upon 2xy minus y square. Hence the result. So in this way, you can find dy by dx. Find the equation of the tangent line to x cube minus 3y cube plus xy plus 21 is equal to 0 at points 1 and 2. That is, x is equal to 1 and y is equal to 2. Now here, function is given. That function is x cube minus 3y cube plus xy plus 21, and that is equal to 0. And if we see nature of the function, this function is implicit function. So we can find dy by dx. Dy by dx is equal to minus dabba f by dabba x divided by dabba f by dabba y. So first we have to find out fx or dabba f by dabba x. So dabba f by dabba x is equal to here x cube minus 3y cube plus xy plus 21. So derivative of x cube is 3x square. Derivative of 3y cube is 0. Derivative of xy is y. And derivative of 21 is 0. And dabba f by dabba y is equal to, so derivative of x cube with respect to y is 0, and here minus 3y cube, that is 3 into 3, 9, y square plus x. So dy by dx is equal to minus, we have here 3x square plus y upon minus 9y square plus x. So dy by dx at 1, 2 is equal to now minus x is 1, so we get 3, y is 2, so we will get 2 upon y is 2, so minus 9 into 4, that is 36, minus 36 plus 1. So here minus 5 upon minus 35. So it is 1 by 7. So this is slope. Let us call this as m, slope. Now if m is slope of the line at point AB, then equation of line is y minus b upon x minus a is equal to slope. Now here y minus 2 and x minus 1 is equal to 1 by 7. So we get here 7 y minus 2 is equal to x minus 1. So 7y minus 14 is equal to x minus 1. So here I can write here x. So take this on this side. So x minus 7y plus 14 minus 1, 7y plus 14 minus 1, that is 13, plus 13 is equal to 0. So x minus 7y plus 13 is equal to 0. What is this? This is equation of tangent line to this curve at point 1 and 2. So this is about implicit function and derivative dy by dx from implicit function. So in this lecture, I have covered maxima minima for single variable function, maxima minima saddle point for two variable function, as well as implicit function. In the next lecture, I will cover problems on partial differentiation. And in last lecture, I will take MCQs. So in last lecture, I will take cover MCQs on partial differentiation. So thanks very much for this lecture. Thanks again.